Yeah, so for everyone online, thanks for bearing with us. Today we're joined by Georgios Chochlakis, a fourth-year PhD fellow at USC, invited by Professor Srikanth Narayanan in the Signal Analysis and Interpretation Lab. His research includes using LLMs to model subjective tasks like emotion recognition, and using LLMs with setups including in-context learning, chain of thought reasoning, and instruction fine-tuning. So everyone, welcome Georgios, and happy to have you.
Yeah, happy to be here. Are we going to go until 12 sharp or 12:10? 12, okay, so I'll try to speed through some of the less important slides. So, hi everyone, I'm going to talk about today why larger language models struggle with subjective reasoning. And bear in mind that this is evolving work, so some models and benchmarks are not always consistent between slides and experiments, so excuse these inconsistencies. I would first like to talk about what problems we're actually dealing with, try to somehow define them. So mostly trying to deal with complex subjective language tasks. And by complex here, we mean tasks where it's inherently difficult problems that have multiple interrelated labels that can be easily confused with one another. I bring as an example anger, disgust, and contempt, where we have seen in data sets the annotator agreement may be high, but the correlation between them is also high, so they tend to co-appear in the labels, even if the one or the other is distinctly present. And with subjective, I mean settings where people can reasonably disagree about the interpretation of a stimulus. In this case, it is a language document, or a different definition could be that we have different yet valid reasoning chains that lead to different yet valid, again, annotations. As an example here, I would like to mention, for example, Euclidean and non-Euclidean geometries. These only differ in axioms, and thereafter they use the same reasoning, which is math, to arrive at different conclusions about space, yet we would consider both of them to be valid. And examples of complex subjective tasks here are emotion recognition and moral foundations. This is what we'll be dealing with in this presentation. So I would like to talk about the sources of variance that we see in these settings. The first one is, as we've already mentioned, is subjectivity. This is the genuine variance we would like to model. And this can stem from differences in interpretation or assumptions, etc., between different people. The second one could be taxonomical errors. That's on the part of the dataset creation. So there we can have underspecification of the labels, causing them to be easily confused with one another. We may have a lacking taxonomy. So there is, for example, an emotion that should have been in the taxonomy. It's not there, it's very prevalent, and annotators need to map it to one of the existing ones, causing confusion. Then we have ambiguity, which is underspecification of the input. For example, when we're dealing with social media data, we usually lack relevant context to make judgments for a specific tweet or Telegram message. And that's not only for the annotators, that's also obviously a problem for the models themselves. And finally, we have genuine judgment errors. This is on the part of the annotators, where they may find some specific tasks difficult, they may be lacking attention. We may have annotator fatigue after annotating a lot of examples, etc. So to motivate my work, yes, we have large language models that have revolutionized natural language processing with their emergent ability to perform in-context learning. So I demonstrate a very simple example of what in-context learning is on the right, where we have an input, then we have an answer as a demonstration to the model. This would be considered a training example in the like traditional machine learning setting. And then we have the query which we want to classify for and expect the model to adhere to the format that we provided, as well as learn from the demonstrations that we have provided in the prompt to give us an answer. And so we essentially question here whether this can be used to effectively model subjectivity. But furthermore, chain of thought prompting, which is in-context learning usually, but not necessarily, plus the enabling of reasoning in LLMs, has seen to improve performance on a range of arithmetic, common sense, and symbolic reasoning tasks, because having a model break the problem into smaller and easier parts with a definite reasoning chain incorporates the steps of the solution in the context of the model, making it easier for the model to predict the final answer. So again, we question here whether this can be effectively used to model subjectivity. And unfortunately, in some initial results that we found very poor subjective modeling in large language models. Here I'm showing indicatively a couple of benchmarks and a lot of LLMs and DMAX, which is a BERT-based model, a much smaller model which has been trained on the data, and you can see its performance with 3 metrics, higher is better, on the rightmost gray bar, how it significantly outperforms all of the LLMs. And I'm going to talk about more details here later and more results.
What are the tasks in the?
These are the top row is moral foundations on Reddit, and the bottom is emotion recognition on Reddit.
Thanks.
Furthermore, motivating us is previous work where it has been shown that integrating a lot of noise in the prompt of a large language model does not seem to affect its accuracy, at least much in specific settings. So namely, on the left-hand side, you see the performance of a large language model with the blue bars, the leftmost bars, when no demonstrations are included in its prompt. So that, well, that's what we would call a zero-shot setting. With the middle orange bars, we see the performance of the model when we have in-context learning. So when we have examples in the prompt of the model of the task, and given the proper ground truth labels that we have for the data set. But what's surprising is that on the right-hand side, the red bars, we see the performance of the model when random labels are provided for the examples in the prompt. And we can see that there is minimal impact in performance. And in fact, there is a setting here where performance is actually increasing with the random labels. So on the right, follow-up work showed that if you see the top right, showed that if you keep scaling the number of examples with random labels, for some settings, you may get degradation in performance that's notable compared to the ground truth labels. That's the blue and the purple lines there. And on the bottom right, you can see how sentiment performance changes as we flip more and more labels in the prompt from positive to negative or vice versa. So you see there is some ability for the models to cater to random quotes labels. However, here, because they use, for example, binary settings, we question whether the model is doing any learning on the actual semantic of the labels or whether it learns that there's been a wordplay switching positive and negative. And so here we want to state that if models can indeed perform tasks with random labels, then in this specific setting, at least, they are performing recognition and not performing any learning. Namely, by randomizing the labels, we are eliciting the prior knowledge of the task for the model, which we will henceforth call task priors. And we want to look at not how this scales with more examples necessarily, but we also want to look at how these priors affect the posterior predictions of the models. And do the model predictions change when we provide random labels compared to gold labels, or is the model getting better at some things and worse at others? And finally, for chain of thought, although it showed a lot of promise, there's been some work showing that it can be unfaithful. And what we mean by unfaithful is that it may not reflect the true causal factors leading to the decision that the model makes. So here I'm showing an example from a paper where they manipulated the prompt of the model and they made specifically its correct answer to be choice A. And you can see in the middle column what was the original answer of the model with mixed responses in the prompt, and what was the answer of the model is with the biased context is on the right, where the model again picks A because that's all it has seen in its context. However, A is the wrong answer, and you can see that the model has rationalized it as saying that a specific phrase does not occur for a specific sport, which is false. And it knows that because with unbiased context, the model was able to predict it correctly. meaning that the model picked A because A was shown in the context, but it showed us like a reasoning chain that was not, again, faithful to the actual reasons it predicted A again. So I'm not here to suggest that humans are always faithful and reasonable and we can count on them when they're providing their reasonings, because we are rationalization machines. Sometimes we arrive at answers first and then provide the reasoning for them. But this has been shown to be the case for large language models as well. So the hypothesis we have formed is that LLMs mostly leverage their pre-existing knowledge for tasks, and that's fine for objective labels, where examples are mathematical problems or entity recognition, which are settings that have a definite correct answer. They have very low disagreement between annotators, and therefore we expect this knowledge to closely align with the prior of the model. Whereas for subjective tasks and subjective labels, like the ones we're dealing with, the annotations could actually vary widely depending on the annotation manual, depending on the subjectivity of a specific person. And therefore, we've hypothesized that the model would not be able to be catered to complex subjective tasks if they don't align a priori with the model.
So in those early works that showed random labels actually improve report, do you know what kind of tasks those were?
They tended to be more objective tasks. When they were talking about subjective tasks, there was actually some sentiment prediction, as I mentioned, which was actually binary. It wasn't even three-way. And there was actually some binary hate speech prediction as well. So they did have some subjectivity, but the binary decision made it much easier for, so much lower disagreement, I suppose. And a TLDR for my presentation is that we quantify the similarity between the prior and the posterior predictions in multi-label settings, so complex settings. And we do so even for API-based models like ChatGPT or Claude, using in-context learning and chain of thought prompting. We saw that larger and more capable large language models actually show larger pool of the priors and the posterior predictions. And basically that the model seems to be ignoring the evidence in the prompt, even if it's in contrast to its priors. And we also evaluate some potential confounding factors, like the consistency that the priors might have over the posteriors, or maybe because of the annotation aggregation that's happening in subjective settings where disparate annotations from different people may be aggregated to arrive at some hotspots aggregate. And we saw that they actually do not account for the entirety of the effects that are observed. And in fact, a very small amount of the effect is only explained by these factors. So I want to go into our methods and try to at least carefully give you a sense of how we try to control for various confounding factors by talking about how we actually elicit the priors of the models, how we checked for consistency and similarity between different model predictions, how we check for how annotators influence the large language models, look at what the metrics we use and what large language models we use. So first, very briefly, I'm going to talk about how we actually sample the prompt to elicit the priors. And so we do this in a specific way, which is we try to sample the labels independently from the text samples that we sample from the dataset, but we do sample both from the dataset itself. So for example, we do not do Bernoulli trials on the label set, but rather choose to sample a random label from the dataset because we have multi-label datasets and we would like to maintain the label relationships. So even if we sample labels randomly, anger and contempt are still more likely to appear together compared to anger and love. And we do the same for also the reasoning chains. So we sample reasoning chains from the dataset itself. We have hand annotated the reasonings for its example and its label, but we sample that independently, both from the text and the labels. So I'm showing an example that was from an actual prompt that we used, where the input is criticizing Le Pen as being alt-right and very dangerous for peace. So it specifically mentions peace and war. The reasoning that was sampled is talking about LGBT issues, and the final label that is shown to the model is none. whereas the input clearly indicates that we're talking about care, and specifically the vice of care, which is harm. And the reasoning clearly also indicates, because we specifically try to include the moral foundations in the reasoning chain, it indicates, again, harm and equality. In our efforts to standardize the prompts and make experiments truly comparable, we follow a strict sampling regime for examples and labels. We perform multiple runs over the evaluation set to increase confidence in our findings, keeping examples the same as well as the labels in the prompt within each run, but across different runs, we use two different methods to resample. In the first, denoted by prior, which you can see on the left-hand side of the table, we completely resample both examples and labels across different runs, whereas in the second, denoted as prior labels, the second column of the table, we resample only the labels between different runs. So while in the first case, different examples can provide perhaps different evidence for the domain of the problem to the model. So to give you an example here, when we are dealing with moral foundations from Reddit, the comments were sampled from various subreddits, targeted subreddits, and therefore, which subreddits the comments are coming from in the prompt may influence the model's decisions. Whereas for the labels, if when changing only the random labels, the task recognition priors should not be affected, here with the caveat that we need to have enough examples in the prompt so that the label distribution roughly remains the same. So we check both settings because we want to explore the sensitivity to the different aspects of the prompt of the models. And we also want to know that if these priors are indeed very consistent across runs, then we can truly call them Bayesian priors. And we do the same for chain of thought independently, again, from the labels. So yeah, I would like to highlight here the examples between different runs are the same, and only the labels, as you can see, change for how we randomly sample them. And similarly for annotator comparison, we keep examples the same and vary only the labels that they provide. So in this case, we have found the common set of examples between annotators. We have kept examples the same between these annotators and only changed their labels in the prompt. For metrics, very quickly, we're using the card score, which is the intersection over the union, and two F1 scores, micro and macro F1 score. And notably, these are all symmetric functions, which means that we can use them to both to measure performance, so namely predictions compared to ground truth, but we can also use them to quantify similarity between models and runs. And what I mean by this is because they're symmetric functions, it doesn't matter which argument you present first and second, the value of the function is going to remain the same. And therefore, we can present predictions from one model and predictions from the same model, but with a different prompt, and compare them with the card score or F1 scores without making arbitrary decisions as to the position of the argument. And by consistency in this work, we denote the similarity between different runs of the same model. And for the models, we have Google's Allen AI's Olmo, Meta's Llama 2 and 3, and OpenAI's ChatGPT 3.5 and 4. And I showed you some baseline results from DMX, which is, again, a BERT-based fine-tuned model. So datasets, again, very quickly, SemEval 2018, 11 emotions in a multi-label setting. And these include tweets. Go Emotions has 27 emotions in a multi-label setting, but we pulled them down to 7 for efficiency, and because initial experiments with all 27 emotions showed very low performance in LLMs. And this dataset contains Reddit comments. And we also want to point out that this is a dataset where they have released the annotator-level label, so we can perform manipulations with respect to the annotators. And finally, we have MFRC. This contains the newest taxonomy of 6 moral foundations compared to the earlier 5 moral foundations. These, again, are Reddit comments. And again, we have annotator level labels here to experiment with. So for the results, I'm first going to show the baselines again for an extra benchmark, actually. And then we're going to talk about how much we actually improve from the priors of the model when we provide gold labels. We're going to compare the posteriors and the priors in in-context learning and chain of thought. And we're going to look at finally the confounding factors, which are potentially consistency and potentially the aggregation of the annotations. So first of all, the baseline, we can see that DMOOC significantly outperforms models in in-context learning and chain of thought in all benchmarks. Again, the BERT-based model is the final bar, the final gray bar. And you can see that in every setting, it's superior, clearly superior to all of the LLMs that we test with. So again, this was part of our motivation, trying to figure out why that was happening. And the first experiment we ran is we tried to check how much we actually improve over in-context learning priors. So here I'm showing 2 rows of results. So it's one for each of the 2 data sets that we test with, SEMAVAL and Go emotions, and we have 3 columns, one for each model we saw. Note that from left to right, we go from less to more capable models, and we have skipped some of the other models for brevity. On the y-axis, we plot the relative improvement of the posterior compared to the prior, whereas the x-axis, we have the number of examples in the prompt. And here you can see that, especially for the smaller Llama 2 13 billion model, we go from negative improvement, which means degradation compared to the prior, to increasing posterior performance, which means that more examples give better evidence to the model, and therefore it improves performance. Whereas when we go toward the bigger models, you can actually see that the improvement is kind of grounded to 0. So for the bigger models, especially meaning for larger models, we see that we get not much improvement when we provide the gold labels. So that's the first piece of evidence. And secondly, yes.
Best task prior, that's like 0 shot?
That's the proxy task prior that I described earlier with the random sampling.
Okay, got it.
And here for the same models and data sets, we present the similarity of the posterior predictions to the ground truth, which is the performance of the model with green, and the similarity of the posterior to the prior predictions, which is orange. Again, on the x-axis, we have the number of demonstrations in the prompt, but it also now contains all 3 metrics. And on the y-axis, it's just the value of the metric. To more easily digest the results, you can just focus on the difference between adjacent green and orange bars. And that makes the effect clearer here, where you can see again on the left-hand side, Llama 2 13 billion, the similarity to the ground truth is roughly equivalent to the similarity of the prior. And whereas the green bars, as we move to the right, do not change much, you can see that the orange bars actually start increasing and increasing, becoming much larger than the green bars for GPT 3.5. This means that the predictions of the models remain very similar to the priors for larger models, whereas for smaller models, they do not influence the posterior as much. So I want to show you here, we saw that the prior has sampled to the posteriors. Here I try to take it to the extreme with the following experimental manipulation. We actually included the query that we want to test for as the first demonstration in the prompt. So you can see the first example includes the query that we find on the last example as well. We include the label of the example in the prompt, and then essentially we ask the model again to predict it. So in effect, if the model wanted to solve the task perfectly, all it had to do was copy paste the label that was shown to it in the prompt. However, when you look at the results on the right, and I'm going to explain what is shown there, you can see that that's not the case. The Jacquard score is never 100% perfect. So you can see 3 experimental settings there. First is ground truth query, where the label of the query is the ground truth. So we present the gold label for the example in the prompt. When we do a random query, the blue bars, there we randomly sample the label of the query in the prompt. So instead of sadness there, it would be love, whatever, something random, again, sampled from the data set. And finally, the green bars, random query with respect to ground truth, is how similar is the final prediction of the model for the query compared to the ground truth, when the model is presented the random label for the example. So is the setting clear here? Okay, so for GPT-4,
Quick question.
Yes, yes.
From the last slide.
From the previous
chat.
slide?
I think so. From the chat. Are you aggregating the labels for each sample? You mentioned the tasks are subjective. Are you analyzing the subjectivity and the non-aggregated annotations?
So we'll look into this later. For now, that's just the aggregate. Yeah, thanks for asking the question. So again, here we're dealing with the aggregate again. So you can see that for GPT-4, the performance of the model in copy pasting the ground truth label is roughly 85% accurate. So 15% of the cases, we can say that the model is essentially refusing to copy paste the label in its output, which is interesting in itself. What's more interesting is if we look at Llama 2 70 billion, this model is 95% accurate in predicting the gold label. So it seems that Llama 2 is more willing to follow instructions, and it seems that there is some overwriting based on the priors for GPT-4. It becomes much more evident, though, when we randomize the label that we give the query in the prompt. So if you see with the middle blue bars, when we do the experimental manipulation for GPT-4, GPT-4 is actually dropping to random levels of performance, even though the label, again, is shown to it in the prompt. We present a random label to it in the prompt, and it's performing at roughly 40% accuracy for the label that it's shown to it in the prompt. And so I think the interpretation here is clear. The model is refusing to copy paste random labels because they do not conform with its prior.
So it's stubborn.
It's stubborn, yes. That's not the case for the smaller and less capable Llama 2 70 billion, where you can see the blue bars are much higher, much closer to the ground truth. It does show, again, some pool of the priors, again, for that model even, but it's not as large as it is for the larger and more capable model. And I think it's very interesting to see that for the green bars, or for GPT-4, the model's predictions are actually closer to the ground truth than they are to the random labels, even though the random labels are presented to it. So you can see the green bars are higher than the blue bars, whereas on the right-hand side, obviously the similarity to the ground truth is less than the random labels because the model is so good at copy pasting random labels. But it's also interesting to see the green bars are a little bit lower for Llama 2 compared to GPT-4. So Llama 2 resembles the ground truth less and the random labels more compared to GPT-4. So it shows you that larger models cannot even copy paste labels they disagree with, let alone infer them when you're doing in-context learning. And so far we've been talking about in-context learning and not chain of thought. So I want to mention here as perhaps a caveat that, okay, we are randomizing the labels in context learning. This is supposed to be a very salient point in the prompt, but it affects very few tokens because the examples are usually much longer than the labels themselves. So noise is injected in very few tokens of the prompt, even though, again, we can agree that it's a very salient point. However, for chain of thought, randomizing the reasoning chain as well as the label not only introduces noise in salient parts of the prompt, it only introduces noise in a very large percentage of the tokens in the prompt. So we ask, is all this randomization going to create, is going to induce priors to chain of thought as well, or is it going to completely collapse the predictions? And here, just to set up the results, I want to begin with some definitions to make the results easier to parse. So we denote performance as being the similarity of the chain of thought predictions to the ground truth. And we also denote consistency to be the similarity of the chain of thought performance to the same chain of thought, but using different but valid reasoning chains. So we had two people work independently to produce valid reasoning chains for this example, and we want to see how consistent the predictions of the model are depending on the different reasoning chains. So the first result I want you to look at is that, again, as we go from left to right, is the similar setting as the results I was showing before. We have the metrics on the x-axis and the value of the metrics on the y-axis. So you can see as we go from smaller and less capable models on the left to more capable models on the right, performance starts to drop significantly lower compared to the similarity of the chain of thought predictions to the in-context learning prior. So you can see that the in-context learning prior has actually a large effect on even the chain of thought predictions of the model. So again, if you look at llama 270 billion, the performance of the model, the similarity to the ground truth is actually higher than it is for the similarity to the in-context learning prior. However, for GPT-4, you can see that the similarity to the in-context learning prior is much, much higher than the performance of the model. So we're seeing the same pattern when we are evaluating this as well in large language models. What's very interesting is to see that the same effect is happening for chain of thought with both random labels and random reasoning chains. So performance as we go from smaller to bigger and more capable models is actually much less than the similarity of the posterior of the chain of thought to what we now can call the reasoning priors of the model. So that's the chain of thought prior of the model. So again, notice that the red bars start becoming much larger than the blue bars as we move from the left to the right. And finally, what's also very interesting is that when we look at the consistency of the predictions, these are again on par, the consistency on par with the consistency that we see between prior and posterior of chain of thought. So that tells you that the chain of thought for larger models also has priors that tend to ignore the evidence that are provided in the prompt, and these priors are just as consistent as if we were using a different but valid reasoning chain. So it kind of shows you that larger language models not only tend to ignore input labels, but they also tend to ignore your reasoning. And in subjective tasks where this can change between different people, that's an issue when we're trying to do annotator modeling or do personalization.
So if they're like so stubborn, can't you like prompt them to be not stubborn? Like tell them like, don't be stubborn, you know, I'm going to give you evidence.
Okay, well, I haven't tried this manipulation like that. We have done other experiments where we try to tell the model, we've done something like this. We tell the model, I'm gonna also give you your prior prediction. And when it's wrong, I'm gonna point that out that in the labels, I'm gonna have, these are the ground truth labels, and this is what you predicted and you're wrong in this. And we actually see that it doesn't, the performance is not improving.
So try shaping them, maybe.
Yeah, I don't know, yeah, perhaps. So after these are our main results here, we are now going to proceed in looking in potential confounding factors. The first one being the consistency. We already saw some results for consistency, but here I'm going to go into more detail. So again, to recap, models do not improve upon their prior, and it's largely because they ignore the evidence in the prompt, and the posterior is almost identical to the prior. So the first question we ask here is, could this be explained away by the consistency of the priors? Namely, the models may have erratic in-context learning predictions, but may have very consistent priors. So namely, when I was showing you this experimental manipulation from one run to the other, when we're doing that with actual gold labels, perhaps we may be getting very erratic predictions. This has been shown in the past that LLMs may have a large standard deviation in performance when changing the examples in the prompt, whereas when we're dealing with the prior of the model, randomization of the labels, maybe the predictions remain the same across different runs. So we in fact find that task priors are not more consistent than in-context learning predictions. So here, again, you can focus on looking at the difference between adjacent bars. So these are groups of 3, where we are showing the consistency of in-context learning, consistency of prior, and consistency of prior labels, the 2 experimental manipulations. So you can see that prior labels is a tiny bit more consistent than priors, as we expected, because we only changed the labels, but it's not a major effect. The most interesting thing to see is that in-context learning tends to be just as inconsistent across runs as the priors are. So the consistency of the priors is not the confounding factors in the effects we see. And we also see that we actually tend to start to achieve higher consistency for larger models. So you can see that the absolute value of the bars going from left to right, from llama 2 to GPT-3.5, the bars are beginning to grow in magnitude, which makes us question whether we may asymptotically, as we increase the capabilities, converge to Bayesian priors. Would be interesting to check and try to analyze what that would mean for large language models. And after we checked for consistency and find that it's not a confounding factor, we ask perhaps that aggregated labels may hurt performance because, for example, it may create hotspots of different perspectives within a single example. So to give you a sense, in a multi-label setting, different annotators may have different labels, but they may have one common label. So when you aggregate, you're going to keep this one common label and you're going to get rid of all the other labels that each individual had picked. I've actually seen it happen, like you can see it happen in some of the aggregations that are happening in the data set. The other thing that could happen is that different annotators or different groups of annotators can prevail in different examples. So here I like to talk about the simplest thing I could think of, which is Republicans and Democrats. If you have some examples in the dataset where more Democrats ended up annotating and therefore they prevail in the aggregate, and some others where Republicans are annotating and prevailing in the aggregate, then when the model sees all these annotations, it may be seeing a hotspots of Republican and Democrat opinions, creating some artifacts in the labels. And finally, we may have other annotation artifacts that may arise from the specific design of the aggregation process. It's not only majority vote. Sometimes you do other manipulations to arrive at the aggregate. So these are, I guess, non-linear effects, and we don't know how they exactly affect performance. I'm reminding again of the experimental manipulation. So the result you'll see is same examples in the prompt exactly, same queries, and the only thing that changes is the annotators labels, the labels that a specific annotator has provided for the specific examples. And the first result I'm showing here is comparing annotator similarity with the prior of the model compared to annotator similarity with the aggregate. So we have the similarity to the prior for each annotator on the y-axis and the similarity to the aggregate on the x-axis. And so you can see that we mostly have negative correlations between these two metrics, which means that the better aligned an annotator is with the aggregate, the less aligned they tend to be with the prior. So this is the kind of a first indication that something might be happening with the aggregation process. So we evaluate this further by looking at how performance varies with respect to prior similarity for each annotator. So here we look at annotator performance within context learning with respect to annotator similarity with prior. The performance is on the y-axis and the similarity to the prior is on the x-axis. Here, predictably, better prior essentially leads to better posterior. So no surprises here, all correlations are positive. However, we want to point out that if you look at the aggregate, it's only 22nd on the 22nd percentile in posterior performance, showing that most individual annotators are actually performing better than the prior is performing, showing further evidence that there is something happening with the aggregate in these data sets. Furthermore, within the same context, we look at the relative improvement that we get from prior to posterior when providing the gold labels for the annotator and contrast that with the similarity that the annotator has with the prior. And here, surprisingly, perhaps or perhaps not, depending on what your expectation was, we see that a worse prior leads to better improvement, as all significant correlations are negative and we see very weak positive correlations in our data. So again, this means that if you have a worse prior alignment, you're going to receive better relative improvement. However, what's interesting to see is even though the aggregate was one of the worst performing mappings with respect to its prior alignment, we can see that it stubbornly does not get a decent boost in performance when we present its labels to the LLM. So the aggregate seems to be the only essentially mapping that goes against the trend of receiving better improvement given its worse alignment. So again, this is, I find more evidence for the fact that the aggregate causes artifacts in the prompt. Yes.
So each point here is a different annotator.
Yes.
Right. So how many labels, how many judgments do you need from this?
We went up to 45 for each annotator. It was difficult to find enough common examples between many different people because the examples were assigned randomly to them.
Oh, I see. So this is on the same examples, right?
This is exactly on the same example.
Right. Okay, got it. But do you think that so it's all very few people? Do you think this generalize to other?
Yeah, the thing is, for example, for Go emotions, I only managed to find, for example, 2 triplets that had enough common examples, and everybody else was so dispersed I couldn't find enough to actually do a proper evaluation because I need enough examples in the evaluation set as well to keep the query the same. So you would need to collect the dataset with that specific purpose in mind, I think, to be able to do larger scale evaluations. Here I was able to try to work with whatever I had in the datasets. And here I'm not going to go into details into these results, but we look at how performance and improvement varies compared to the similarity to the aggregate that its annotator has. And we very expectedly by now find that the more like the aggregate an annotator is, they have both worse performance and they also receive less improvement from the model. Okay. So you can see basically if you look at the trends here, we present the results in the paper. All significant trends are negative and most trends in general are negative even if they're not.
There's some wood going on.
I'll stop sharing and maybe reshare.
Yeah.
Okay, it's not about. Oh no. Is it actually?
Well, the good thing is I'm done showing results, so I can just talk over the remainder of the slides, but I won't be able to go back and talk over slides with people if we want to discuss something specific results.
I mean, do you see it on Zoom?
No, it's off.
No, it's on Zoom. Okay. I also never happened before, actually.
There. I unplugged and unplugged it and plugged it in again. Okay. So to summarize our aggregation experiment, we find that aggregate has low prior alignment, which is the first indication that something is happening with the annotations. But we find that despite models with worse alignment receiving bigger boosts, and by models here I don't mean the large language models, but the model of the annotator, we find that the aggregate receives smaller improvements and that looking more like the aggregate also results in smaller improvements and overall worse performance. And but if you look at more closely at the results that we have specifically in the paper, you find that these observations don't actually account for much of the gap between LLMs and BERT-based models, but account for like a small percentage of the effects. So it looks like it's not a major confounding factor. It is one, but not a major confounding factor in looking at the pool of the priors on the posteriors for large language models. So for the general takeaway, yeah, I just want to point out here that it seems that counterintuitively, as large language model size, data usage, and training time and stuff increases, we actually see that in-context learning and chain of thought ability decrease. As in, again, if the larger models may be doing better task recognition, may have better priors, but in terms of doing actual learning, as the name of in-context learning suggests, we see a decreased ability to do so, as predictions more closely resemble the proxy priors of the models compared to the ground truth. And despite the sensitivity of the task priors themselves to the prompt that's used to elicit them, so we saw consistency is as low or as high as for in-context learning. So this work is presented from these 3 papers, 2 of which are under review right now. And I want to thank my collaborators in these works. And now I can take, for 5 minutes, I can take questions.
Past 12 because we started late.
Okay.
Maybe a high-level question to no one is how sort of feasible do you think it is that LLMs are like the right tool to like model human performance in this task or exceed it?
I'm not convinced that the in-context learning is gonna solve the issue. We are experimenting with other techniques. As I said, as Christina suggested, there may be clever prompting techniques that can boost performance a little bit. If there are any, we haven't found them yet. We haven't found anything consistent. Fine-tuning is actually helpful. It improves performance quite a bit. It still doesn't reach the levels of much smaller models like BERT. I do feel like LLMs do hold some promise, but it seems that the current regime, the current setting where as people found that, for example, chain of thought improves performance in models because it enables reasoning, in quotes, allegedly. They started integrating more and more chain of thought examples in the training of the models themselves. So I think that's why the models may be developing these sort of priors, because as I think has been very compellingly described, like LLMs are perhaps the best databases we've ever created, but that doesn't necessarily mean that they can solve novel tasks. And so as soon as you make like something part of the database, then the model is going to be able to retrieve that instead of trying to like do any sort of quotes learning. So I do think they hold promise, but I'm kind of not optimistic given current training paradigms. It remains to be seen though. Okay.
So basically, like the way, so it's much easier to align a simple model like BERT, for example, align it to kind of the emotion, to the data.
Yeah.
Rather than like more like, so we might actually get some benefit of the vast prior knowledge, but we can't align it to like more kind of bespoke or more outside of, you know, something about emotional recognition that's not reflected in the priors.
Yeah, I think that there is a very definite trade-off here where we see that BERT is going to have a better performance for datasets we care about. But as, for example, is the case for the project we are together working on, where we're pivoting from this setting to the other setting and then to the other country and the other language, then perhaps LLMs are the more scalable way to approach this problem, because yes, you will have some decrease in performance if you were to evaluate it in your data set, but you do not need any retraining. You do not need thousands of data points to cater the model to it. So it definitely has its like LLMs have their merits in terms of like this prior knowledge that I seem to be criticizing in this work, but it's actually why we're using them.
But so can you speculate on how does it affect like knowledge distillation, which is the trend right now that you're familiar with, where you use LLMs to create more examples to like to align the smaller models?
Yeah, I think knowledge distillation in itself probably needs to be aided by other guardrails, like looking at the confidence of the models themselves, or perhaps I know you have worked in your lab where you look at, or we were talking about it, you look at the confidence of a smaller model on the predictions for the specific examples. And these are the models you use. So you definitely need to do a lot of filtering to get the most out of smaller models. But yeah, trying to find the appropriate data set and have LLM essentially assist you in its labeling, I think it's very promising and something I'm working on currently, not the labeling itself, but as you know, label verification. Trying to use LLMs to try to capture as much of the variance that I mentioned in the beginning and try to discard as much of the judgment errors from annotators. So I think they are definitely very useful tools, but they need to be taken with a grain of salt when interpreting results.
I just want to understand more correctly. So you have in context these actors from some kind of distribution. and you want to LLM to make a prediction that has a similar distribution to this example. Right?
Yeah.
And is there any distribution if you just center the random input and random output?
That's why when we're sampling from the data, when we're sampling random labels, if that's what you mean, we are sampling them again from the same data set. So you have XY pairs in the data set. What you usually do is sample the pairs together. So basically a joint distribution. What we do is sample X individually and then independently, completely from X, we sample Y to provide random labels. So the label distribution that the model sees in the two settings are exactly the same. Is that what you were asking about?
Yes, sir. I was just curious about whether we can measure some kind of correct distribution from this randomly picking up the input and the output randomly to create in-context examples, and whether it is like makes sense to compare the outputs, the prediction outputs, using the similarity between
The logics, basically,
yeah.
you mean?
Yeah.
We want to do this. There are two caveats to that. First is that we cannot do that with the most capable models out there, which would be ChatGPT and Claude, etc. And the other caveat is we have a multi-label setting. So there is a bias for the model to produce the labels in the same order they're shown in the prompt. So this creates artifacts where even though the model may be less confident for a specific label, it's still going to have a much larger distribution, like density towards it, just because it's shown before that label in the prompt. So because the labels are usually ordered alphabetically, even if the model wants to really produce a low as its more confident prediction, say if anger is also one of the labels it wants to predict, initially anger is going to have much more density in the predictions because anger starts with an A, love starts with an L. So anger is presented in the prompt, in the instructions before love, and it's going to produce it first. So you need to sift through this as well, and we plan to try to study how this can be done optimally, but it's kind of tricky because of that.
I see. Yeah, because I have two thoughts about this. One is that the words that you mentioned in the related section, they are mostly talking about the pattern recognition of the in-context query. For example, the papers you mentioned is they flipping the label.
Yeah.
Like if you flip the positive to A and negative to B, then prediction will come out for positive for A, negative for B. And so that's why I thought that whether the random selection from the output and making no patterns in the in-context examples can really do a good prediction in the in-context learning setting. And second thought is that I think there are two different behavior from the pre-trained model and instruction tuned. And maybe a recent paper also mentioned that if the instruction tuned models are more affected by the pre-trained knowledge, the semantic parameters, and rather than the instruction tuned model, pre-trained model are more
amenable.
So
to your first point, as a proxy for looking at that, because you said many of the papers of subsequent work for randomization switched to looking at the logics, not the performance itself. And they showed that if you scale it enough, you start to see patterns. What we try to do as a proxy for GPT, for example, is scale the examples and see if the predictions change. And we scaled it up to 85 examples. We saw essentially no difference. So it looks like the effect is stronger. The other caveat there is, as I mentioned, when you're doing manipulations on binary settings, you need to distinguish between the model learning, say, new semantics or new tasks, and the model learning that you're doing a word play between the words that you have there. I think it's much more likely that the model is realizing that, oh, they're saying negative when they mean positive and positive when they mean negative, rather than learning new definitions of negative and positive. Again, that's a hypothesis, but yeah.
But the second thing that in context learning is worse and refines instructions in models than original models. That's interesting.
I'm not sure whether it is bad or good or bad.
Performance,
So
it's
it's
like more stubborn, like you know.
yeah, right.
Instruction tuned models are more stubborn.
Yeah, kind of.
Yeah, I haven't tried a non-instruction tune models for the larger variants. I've tried some 7 billion non-instruction tune models, but we would need to see how scale affects these as well. So I'm not gonna speculate on them. Like, yeah, we can certainly try, especially for llamas, llama 2 and 3, we can do the non-instruction tune.
Yeah, like guardrails make like models more stubborn. So yeah.
We have another question from the chat from Marcus. Did you investigate the ordering of the examples in context learning to see how it affects performance? The order of examples is the greatest effect on how LLMs process them. It might also affect how they integrate info from their partners.
So I didn't do this manipulation for the same examples, but we did see that changing the examples completely in the prompt for bigger models doesn't actually change their predictions. So if the similarity between two completely different prompts is 0.85, I imagine it's going to be pretty high for the same examples in different order.
I think we went a little bit over because we started late. But
yeah.
Thanks everyone for coming. Thanks Georgios for talking.